Okay, now we want to take a look at topic 9.1, which goes into more detail on simple harmonic motion, including the derivations of the sinusoidal behavior in terms of the definition of simple harmonic motion. So here we're going to look at how those equations for displacement and velocity solve the defining equation of simple harmonic motion. We'll look a little bit more carefully at expressions for energy, kinetic energy and potential energy in simple harmonic motion. And we'll see two examples, how the mass on a spring and the simple pendulum are examples of simple harmonic motion, especially when we look at the small angle approximation for a pendulum. Recall that the definition of simple harmonic motion, the defining equation, was that the acceleration was proportional to and opposite to the displacement. Here we're going to make one little change here, and you'll see why this is convenient shortly, and say that the constant of proportionality will be called omega squared. It may feel a little bit strange not to use like omega, or a constant like B or K, something like that. But this omega squared, we'll ultimately see is the angular frequency for the simple harmonic motion that results from this particular equation. And so to solve the defining equation, we're actually looking at a differential equation because two of the variables, the acceleration and the displacement, are related by a derivative. Specifically, the acceleration is the derivative of the velocity, and the velocity is the derivative of the displacement. So the second derivative of displacement with respect to time, or d squared x dt squared, is equal to acceleration, and that's equal to negative omega squared times x. Solving differential equations is really beyond the scope of this course, but it shouldn't take you too much time to, if you're comfortable with calculus, to take the second derivative of either the function x of t is equal to x0 cosine omega t, or x of t is x0 times sine of omega t, are two base sinusoidal functions, where omega is the angular frequency, x0 would be the amplitude of the motion for the displacement, and see that these solve this equation. Specifically, if we take the example with the cosine for the displacement that goes along with the graph we've been looking at carefully, the first derivative, x0 remains a constant. The derivative of cosine is negative sine, and the chain rule tells us we'll have has an omega that comes out in front. So the velocity will be negative omega times x0 sine of omega t. And of course, taking the second derivative, we have the negative omega x0 stays out in front. The derivative of sine of omega t will be cosine of omega t. So there's two omegas now, and you have negative omega squared x0 cosine omega t. But if we look, the x0 cosine of omega t part is just the same as we had right here, which is x of t. And sure enough, that satisfies the defining equation. The acceleration is equal to negative omega squared times x. So that's why we made that choice to say that the constant of proportionality was equal to omega squared, because that gives us a nice form of x of t. The angular frequency, of course, if you go back to some of your definition of these relationships, sine and cosine, is related to the period. Specifically, omega is 2 pi over the period. So for example, in these graphs with a period of 2, the value of omega would be pi. Some key observations about some special features here. One, the period. The period of motion doesn't depend on the amplitude, it's a constant. The values here, x0, could be anything that we want, and the acceleration would be omega squared times that displacement. Make it a larger displacement or a smaller displacement, it doesn't matter. The amplitudes can be looked at for both the amplitude of the velocity, like the maximum velocity that you achieve in the middle of the motion, and the maximum acceleration that you achieve at the far ends of the motion. Just by looking at multiplying omega times x0, and in terms of the acceleration, omega squared times x0, you'll see the units work out because the units of omega are inverse seconds. So this would be meters per second or meters per second squared. This is a kind of convenient thing to know about. If you know the displacement and you know the frequency, you know what the maximum velocity and the maximum acceleration are. And finally, this also shows us where those phase relationships come from. The difference between cosine and negative sine is that minus pi by 2 phase shift. And the difference between cosine and negative cosine is, of course, a pi phase shift, or exactly out of phase. Just so you know that you could do exactly the same thing with sine of omega t, or any linear combination of sine and cosine. So it really doesn't matter what the initial phase is, you can come up with the same relationships here. When we get around to doing some problem solving with simple harmonic motion, oftentimes the trick is recognizing simple harmonic motion in the way that the information is given. Remember, there's only two things that you need to know in order to explain everything about simple harmonic motion. You're going to need to know the frequency of the motion, or the period of the motion, so that you can find the angular frequency omega. And then you'll need one of those amplitudes, the amplitude for the displacement, the velocity, or the acceleration. Any one of those will work to define the motion completely. So for example, you might have an expression, you might have like a graph of the acceleration versus displacement. In this case, the slope will be omega squared. And so you have the angular frequency from this graph. And the amplitude might be given by looking at the maximum or the minimum of the displacement. If you're looking at a graph of either position, velocity, or acceleration versus time, you'll be able to read the period off of the graph. And so you can find the frequency or the angular frequency with 2 pi over the period. And then the maximum velocity here, which would be equal to omega times the maximum displacement, is also pretty easy to read off the graph. And then there might also be just a description of simple harmonic motion. And you really just have to ask yourself, do you have two pieces of information that can help you completely describe the motion? When we start taking a look at specific systems, we can take a look first at the mass spring system. There's a nice link here to a PhET simulation that you can play around with this, but I just want to look at the equations quickly. The restoring force on a spring, like we said before in topic 4.1, is clearly going to satisfy the relationship between acceleration and displacement as long as we have a spring that obeys Hooke's law. If the force is equal to the opposite of a spring constant times x, that means that the force is a restoring force. It points in the opposite direction of the displacement, and obviously it's proportional to the displacement here. The acceleration then matches the defining equation because the acceleration is f over m, which would be minus k over m times x. And so even though it doesn't say omega squared here, it is negative constant times the displacement, which is great. What does that mean in this case? Well, what it means is that because this equation, a is equal to minus k over mx, is the defining equation for the motion of that mass on a spring, this can be equated to omega squared, and the angular frequency is equal to the square root of k over m. And what's kind of cool about this is it tells us that there's two factors that influence what the frequency of a mass spring oscillator is. It's how strong the spring constant is and how large the mass is. It's probably not too hard to sort out what you would expect from your experience with masses and springs. Larger spring constants will give you larger restoring forces, which will increase the rate at which the mass is brought back to center when it's displaced, and larger masses will cause it to respond more slowly. So the angular frequency is proportional to the square root of k. The angular frequency is inversely proportional to the square root of the mass. And if we know what the max displacement is, we can find the maximum velocity just from the relationship we had before. It's fun to do. There's a slightly more difficult analysis for the vertical mass spring system because, of course, gravity gets involved, and at equilibrium, the spring is stretched. But it turns out it gives the same relationship. Omega is equal to root k over m. When we go to the simple pendulum is actually a little bit more complicated because it doesn't end up matching the defining equation. When you think about a pendulum swinging back and forth, perhaps we define the displacement as this arc length that's produced when the pendulum is swinging back and forth, right? On a string, it will follow a circular path. So maybe we call that circular displacement x. And we know that the force depends on the angle. If we look at the tension force and we look at mg, you can break the force of gravity into two components. The tension will be proportional to, will be related to mg cos theta. Just a quick little side note as a hint, the tension is only going to be equal to mg cosine theta at the maximum displacement. While it's undergoing circular motion, you may need a larger tension to provide the centripetal acceleration. But that's not going to end up being particularly important for the simple harmonic motion part of this. Okay, side note done. Coming back to the simple pendulum, what we find is that there's a restoring force that points tangent to that circle that's equal to mg times the sine of theta. The tension force can't provide any restoring force. So our acceleration is equal to F over m, which is going to be minus g sine theta. Well, notice that doesn't match the defining equation for simple harmonic motion, which says that A should be proportional to the displacement. And even if we make the substitution, wisely seeing that the angle theta is defined as the ratio between the arc length, x, and the length of the radius of that circle, so theta is x over L, even if we make that substitution, we're not proportional to x, we're proportional to the sine of x over L. So it's not simple harmonic motion when you look at a pendulum. However, you can make a very good approximation known as the small angle approximation for a simple pendulum. Let's take a look at this in a Desmos. So what I have here, I'm going to turn off a couple of graphs, is I have the graph of the line y is equal to x in black, and I have the graph of y is equal to sine of x. And what I want you to note, and I've also drawn a vertical line here at 10 degrees. And what I want you to notice is that at 10 degrees, you have to zoom in an awful lot before you see the difference between these two. And in fact, let me bring this over. Let me bring my point over to the right spot here. Whoops, I don't have a value there. Oh, I know what the x is. That's right. So when we come to about here, the value of sine of x, this is going to be equal to, whoops, why don't I get it labeled? Hard to see. Oh, here we go. Sine of x is equal to 0.169 when the value of x is equal to 0.17. So here you're still looking at less than 1 part in about 170, so less than 1% difference between sine of x and x. This is what, so we can approximate the behavior of and the value of sine of x as x for a small angle. Obviously, this doesn't work forever. As you zoom further and further out, sine starts to veer downwards, whereas the line, obviously, y is equal to x, will continue upwards with a constant slope. So that by the time you get to larger angles, like 20 or 30 degrees, it is no longer a good approximation. Just because it's useful to think about the small angle approximation for all of the sinusoidal functions, notice that tangent of x, which obviously has that asymptote at pi over 2 or at about 1.5, it also is very well approximated at 10 degrees or below by sine of x. Our differences here are just under a percent, and you can barely see the difference between these lines until you get above about 10 degrees. Cosine, of course, doesn't look anything like these graphs, and so it's not well approximated by x at all. In fact, it stays pretty close to 1 for quite some time, going down to maybe like 0.98 by about 10 degrees. But you can get a really, really good approximation of cosine of x with the function 1 minus x squared over 2. And if you take a look at that graph, 1 minus x squared over 2, you see that even all the way up to maybe like 20 degrees or so, you have very, very good agreement between 1 minus x squared over 2 and cosine of x. All of this is to say that with a small angle, we can make the substitution instead of sine of x, we can just do x. Or in the case of sine of x over L, we can just write this as x over L. So we think about the displacement now as being horizontal instead of along an arc. And we think of the restoring force as being horizontal because the pendulum doesn't move up and down very much. And now our acceleration is equal to negative g over L times x. It's proportional to the displacement and in the opposite direction, and the constant of proportionality is g over L. So this small angle approximation for a simple pendulum does give us something that matches the form A is equal to minus omega squared x. And doing the same thing that we did with the mass and spring, this g over L is equal to omega squared. So the angular frequency will be equal to g over L for a small angle displacement with a pendulum. What's maybe interesting here is that the mass of the pendulum isn't actually important because the restoring force is proportional to that mass, and it only depends on the acceleration due to gravity and the length of the pendulum. The angular frequency is proportional to the square root of g, and the angular frequency is inversely proportional to the square root of L. So here's a couple of examples of problems that are pretty common to solve. You might say, how could you design a pendulum clock so that it has a period of 1 second? Obviously, you would want to think about it as being on Earth. If you took it into outer space or up to the moon, it wouldn't work the same way. And then you could talk about a mass spring system. What would the mass be if you had a period of motion of 0.35 seconds? And of course, those are just going to make use of the omega is root k over m for the mass spring system, and omega is equal to root g over L for the pendulum system. Moving along, however, we also look at energy in simple harmonic motion. Going back to this simulation here, we might remember seeing that, like we did in topic 4.1, kinetic and potential energy exchange places twice per cycle, that you have a minimum at both for kinetic energy at both the minimum of the displacement and the maximum. You have a maximum of kinetic energy at the midpoint, both moving to the left and moving to the right. And it looks like these have a sort of quadratic shape to them. In fact, they do, because if we take a look at the potential energy in the system, it's going to be proportional to for example, in a mass spring system, you have your 1/2 kx squared. Another way of writing that would be m omega squared for k. And so you have 1/2 m omega squared x squared. The kinetic energy would obviously be proportional to v. So you could do 1/2 m v squared, which is 1/2 m omega squared maximum displacement squared, making some simple substitutions. So it turns out that these are quadratic because the expression for potential energy involves a quadratic in the displacement. The expression for kinetic energy involves a quadratic in terms of the velocity. And so we have a few expressions here. I believe this one is inside of the data booklet, not commonly used, but it's nice to have relating the velocity at any point to the displacement. So that we can find where, when we know we are displaced, say at half the maximum amplitude, what the velocity is. So these are quadratic, and they all have a very similar form. Some key observations about energy that we get from that simulation. Total energy remains constant, but switches between kinetic and potential energy twice per period, which we'll see the problem in a moment where that's important. We see that sine squared shape to the graph because kinetic energy and potential energy both depend on the square of the displacement or the velocity. And then energy is equally distributed when the displacement is the maximum displacement divided by the square root of 2. And this occurs 1/8 of a period from equilibrium. When you do problem solving incorporating energy, you'll frequently see a graph that shows what the kinetic energy is as a function of time. Here you have to be careful in thinking through what you're seeing. Kinetic energy is a minimum at, say, the far left displacement. Then it reaches a maximum at equilibrium, then reaches another minimum at the far right. Then it reaches a maximum as it's coming back the other way, and reaches a minimum when it reaches the far left again. So this is a sine squared curve, and the period is not maybe, what is this, 0.175 seconds or so. It's really 0.35 seconds. You have to look for two maxima and minima to find the period to help you do the angular frequency. And then, of course, you can use the expression for the kinetic energy or the total energy to find out what the maximum displacement is and solve a question like this. And finally, just to point out, simple harmonic motion is one of those types of motion that we describe a lot because it shows up everywhere. In fact, physicists really understand this differential equation super well because it helps understand so many oscillating systems or approximations of many oscillating systems. Some mathematicians even talk down to physicists saying they really only know how to solve one type of problem, the simple harmonic oscillator. But it's so valuable because oscillating electric circuits, the behavior of atoms, circular motion, music, all of these can be understood through simple harmonic motion. Good luck working a few problems with this, and we'll connect back again for beginning to look at waves and diffraction.